Welcome to this solution walkthrough. In this session, we'll tackle problem number 1137, titled NTH Tribonacci number. This is a fascinating problem that explores numeric sequences, offering a great opportunity to deepen your understanding of recursion and dynamic programming. Let's dive in and see how we can solve it step by step. The Tribonacci sequence is a mathematical progression similar to the Fibonacci sequence, but with a key difference. Instead of each term being the sum of the two preceding terms, in the Tribonacci sequence, each term is the sum of the three preceding terms. The sequence begins with t_0 equals 0, t_1 equals 1, and t_2 also equals 1. For any term where n is greater than or equal to 3, the value of t_n is calculated as the sum of t_n1, t_n2, and t_n3. Your task is to find the value of t_n for a given integer n. The input will be a single integer n, constrained between 0 and 37, and the output will be a single integer representing the NTH Tribonacci number. To see how the Tribonacci sequence works in practice, consider an example where n equals 4. Starting with the base cases, t_0 equals 0, t_1 equals 1, and t_2 equals 1. Next, we calculate t_3, which is the sum of t_2, t_1, and t_0. This results in 1 plus 1 plus 0, giving us t_3 equals 2. Finally, we calculate t_4 by summing t_3, t_2, and t_1. That is 2 plus 1, resulting in t_4 equaling 4. Therefore, the fourth Tribonacci number is 4. Now, let's look at a larger example where n equals 25. Using the same process, the Tribonacci sequence grows as follows, starting with t_0 equals 0, t_1 equals 1, and t_2 equals 1, we calculate subsequent terms iteratively. t_3 equals 2, t_4 equals 4, t_5 equals 7, t_6 equals 13, t_7 equals 24, t_8 equals 44, and so on. By continuing this pattern, we find that the 25th Tribonacci number, t_25, equals 1,389,537. This demonstrates how the sequence grows rapidly as we calculate higher terms. Finally, let's consider some important constraints and edge cases. For the smallest input, n equals 0, the 0th Tribonacci number is directly 0 by definition. For the largest input, n equals 37, the result is guaranteed to fit within the range of a 32-bit signed integer. Intermediate cases include n equals 1 and n equals 2, both of which return 1 as per the sequence definition. For any n greater than or equal to 3, the Tribonacci number can be computed iteratively or recursively by summing the previous three terms. These edge cases and constraints ensure the problem is well-defined and manageable within the given input range. To compute the NTH Tribonacci number, one straightforward approach is to use recursion. The Tribonacci sequence is defined such that starting from t_3, each term is the sum of the three preceding terms. This makes recursion a natural choice, as we can define t_n in terms of t_n1, t_n2, and t_n3. For the base cases, t_0 is 0, while both t_1 and t_2 are 1. While this approach is simple to implement and aligns well with the recurrence relation, it comes with significant trade-offs. The key issue is that it has exponential time complexity, 3 to the power of n. This is because the same subproblems are recomputed multiple times, leading to a lot of redundant calculations. For small values of n, this might be manageable, but as n increases, the number of computations grows rapidly, making the approach impractical for larger values of n, especially near the upper constraint of 37. Thus, while recursion captures the essence of the problem, it is not efficient for larger inputs. A more efficient solution involves using a dynamic programming approach. Instead of recomputing values repeatedly like in recursion, we calculate each Tribonacci number iteratively and store the results. Starting with the base cases t_0, t_1, and t_2, we compute t_3, t_4, and so on, up to t_n, using the formula t_n equals t_n1 plus t_n2 plus t_n3. This ensures that each value is computed only once and eliminates redundant calculations. An important observation here is that at any point, we only need the last three values in the sequence to calculate the next term. This means we can further optimize space by using just three variables to store these values instead of maintaining an entire array. With this optimization, the time complexity of the approach is O(n), as we compute each term exactly once, and the space complexity is reduced to O(1). This balance of simplicity, efficiency, and low memory usage makes dynamic programming the most practical approach for this problem. For even greater efficiency, particularly when dealing with very large n, we can use matrix exponentiation. The Tribonacci sequence can be represented as a matrix equation, where the nth Tribonacci number is derived by raising a transformation matrix to the power of n2. The advantage of this approach is that matrix exponentiation allows us to compute the result in O log n time, thanks to the divide and conquer nature of matrix power calculations. This makes it asymptotically faster than the iterative dynamic programming solution. However, it also introduces additional complexity. Implementing matrix exponentiation requires a solid understanding of matrix operations, and the overhead introduced by these operations can make it less practical for smaller values of n. While this approach is theoretically faster, the trade-off lies in its complexity, which might outweigh its benefits for the constraints of this problem. Given the constraints of this problem and the range of possible inputs, we have chosen the dynamic programming approach with space optimization as our solution. This method strikes the best balance between simplicity, efficiency, and practicality. With a time complexity of O(n) and a space complexity of O(1), when using three variables, it is well suited for computing Tribonacci numbers up to n equals 37. While matrix exponentiation offers a faster time complexity in theory, it introduces unnecessary complexity for this scale of problem. On the other hand, the brute force recursive approach is far too slow and inefficient to be a viable option. By leveraging three variables to store only the most recent Tribonacci numbers, we minimize memory usage without complicating the implementation. This makes the solution easy to write, easy to understand, and highly efficient, ensuring it performs optimally within the problem's constraints. The Tribonacci sequence is an extension of the Fibonacci sequence where each number is the sum of the three preceding numbers instead of just two. To break it down, the sequence starts with three defined base values, t_0 equals 0, t_1 equals 1, and t_2 also equals 1. For any term greater than or equal to 3, the sequence is calculated as t_n equals the sum of t_n1, t_n2, and t_n3. Our goal is to compute the value of t_n for a given n using this relationship. One of the most straightforward methods to solve this problem is the brute force approach using recursion. With this method, we first define the base cases. When n is 0, 1, or 2, we simply return the predefined values of t_0, t_1, and t_2, respectively. These base cases serve as the foundation for the recursive process. When n is greater than or equal to 3, we use the recursive formula t_n equals t_n1 plus t_n2 plus t_n3. This means that to compute t_n, the function will call itself to calculate the values of t_n1, t_n2, and t_n3. These results are then summed up to get the final value for t_n. To implement this logic, we write a recursive function that first checks if n matches one of the base cases. If it does, the function directly returns the corresponding base value. If not, the function makes three recursive calls to compute the necessary preceding values, adds them together, and returns the result. As the computation progresses, the recursive calls form a branching structure. The function starts at t_n, then branches out to calculate t_n1, t_n2, and t_n3, and so on. This branching continues until the base cases are reached. Once the base values are returned, the recursion unwinds, and the intermediate results are combined to produce the final output. To see how this works in practice, suppose we want to compute t_4. Using the recursive formula, t_4 equals t_3 plus t_2 plus t_1. To calculate t_3, the function computes t_2 plus t_1 plus t_0. The base cases tell us that t_2 equals 1, t_1 equals 1, and t_0 equals 0. Adding these values gives t_3 equals 2. Now we can compute t_4 as 2 plus 1 plus 1, which equals 4. This gives us the final result, t_4 equals 4. However, it's important to note that this approach generates a recursion tree, where each node represents a function call. The size of this tree grows exponentially because each call spawns 3 additional calls. This leads to a time complexity of 3 to the power of n, which becomes highly inefficient for large values of n. Additionally, many computations are redundant. For example, t_2 is calculated multiple times during the process of computing t_4. These inefficiencies highlight the limitations of the brute force approach. The recursive approach relies heavily on the call stack to manage function calls. Each time the function is invoked, its state is pushed onto the stack. Once a base case is reached, the stack unwinds, and intermediate results are aggregated to produce the final output. However, this method does not use any additional data structures like arrays or hash maps. Values are computed on the fly and returned directly, which can lead to significant redundancy. To address this, memoization can be introduced as an optimization. By storing previously computed values in a dictionary or array, we can reuse them instead of recomputing, reducing the time complexity to n. Another optimization is to compute the sequence iteratively. This approach eliminates recursion altogether, reducing the space complexity to 1, since no additional call stack is needed. Both memoization and the iterative approach make the algorithm significantly more efficient, especially for larger values of n. This solution computes the nth Tribonacci number efficiently using an iterative approach to avoid the overhead of recursion. The Tribonacci sequence is initialized with the first 3 base cases, t_0 equals 0, t_1 equals 1, and t_2 equals 1. For n equals 0, the function returns 0 directly. For n equals 1 or n equals 2, it returns 1 directly as these are predefined values of the sequence. For n equals 3, the algorithm iteratively calculates the next value in the sequence by summing the previous 3 numbers. The variables t0, t1, and t2 are used to represent the last 3 terms of the sequence, and t3 is used for the current term being computed. After calculating t3, the variables are shifted forward so that t0, t1, and t2 always represent the 3 most recent terms. This method ensures that the space complexity is 1, as it uses only a constant amount of space regardless of the input size. The time complexity is n, because the loop iterates from 3 to n, performing a constant amount of work in each iteration. This makes the solution efficient and suitable for large values of n. Overall, this implementation is concise and avoids the pitfalls of recursive solutions, such as stack overflow and redundant calculations, making it optimal for this problem. This is the Java implementation of the nth Tribonacci number problem, mirroring the logic of the provided Python solution. The code uses a single class named solution with a method Tribonacci to compute the result iteratively. Key differences from Python include explicit type declarations for variables and the use of Java's int primitive type. The iterative approach ensures efficient computation with n, time complexity, and 1, space complexity. Let's begin with an example where n equals 4. First, we check the base cases. Since n is not 0, 1, or 2, we proceed to the iterative computation. Next, we initialize the first 3 Tribonacci numbers, t0 is 0, t1 is 1, and t2 is also 1. Now, we start the iterative calculation. For the first iteration, where the loop counter I equals 3, we compute t3 by summing t0, t1, and t2. This gives us t3 equals 0 plus 1, which is 2. After computing t3, we update the variables so that t0 becomes 1, t1 becomes 1, and t2 becomes 2. For the next iteration, where I equals 4, we compute t3 again using the updated values. This time, t3 equals 1 plus 2, which is 4. Again, we update the variables, t0 becomes 1, t1 becomes 2, and t2 becomes 4. Once the loop completes, we exit and return t2, which holds the value 4. The final output for n equals 4 is 4. Now, let's work through another example where n equals 6. As before, we start by checking the base cases. Since n is not 0, 1, or 2, we proceed to the iterative computation. Again, we initialize the first three Tribonacci numbers, t0 is 0, t1 is 1, and t2 is 1. With these values set, we begin the iterative calculation. For I equals 3, we compute t3 as the sum of t0, t1, and t2. This results in t3 equals 0 plus 1, which is 2. We then update the variables, t0 becomes 1, t1 becomes 1, and t2 becomes 2. Next, for I equals 4, we compute t3 again. This time, t3 equals 1 plus 2, which is 4. The variables are updated again, t0 becomes 1, t1 becomes 2, and t2 becomes 4. For I equals 5, t3 is computed as 1 plus 2 plus 4, which equals 7. After updating the variables, t0 becomes 2, t1 becomes 4, and t2 becomes 7. Finally, for I equals 6, we calculate t3 as 2 plus 4 plus 7, which gives us 13. After calculating t3 as 13, we update the variables one last time, t0 becomes 4, t1 becomes 7, and t2 becomes 13. With the loop complete, we exit and return t2, which now holds the value 13. The final output for n equals 6 is 13. Lastly, let's consider a simpler example where n equals 0. Here, we immediately check the base cases. Since n equals 0, we return 0 right away. The final output for n equals 0 is 0. To analyze the time complexity of our algorithm, we start by examining the two main components, the base cases and the iterative loop. For the base cases, when n equals 0, 1, or 2, the algorithm directly returns the result without any further computation. These operations take constant time, or O1. Now, for n greater than or equal to 3, the algorithm uses a single for loop. This loop executes from I equals 3 to I equals n, resulting in n minus 2 iterations. Within each iteration, we perform a simple addition, t3 equals t0 plus t1 plus t2, which is an O1 operation. Additionally, the reassignment of variables t0, t1, t2 equals t1, t2, t3 is also a constant time operation. Overall, each iteration of the loop requires O1 time. Since there are n-2 iterations, the total time complexity of the loop becomes O(n)(2) multiplied by O1, which simplifies to O(n). When we combine the base case operations and the loop, the overall time complexity of the algorithm is O(n). Now, let's evaluate the space complexity of the algorithm. This solution uses a fixed number of variables to compute the Tribonacci sequence. Specifically, we have t0, t1, t2, and t3, which are all integer variables requiring O1 space each. Additionally, there's the loop counter I, which also uses O1 space. The input variable n does not add to the space complexity since it's provided as part of the input and doesn't require additional storage. Importantly, the algorithm does not use recursion or any extra data structures. Unlike a recursive approach, which would require stack space proportional to the depth of the recursion, or an approach using an array to store intermediate results, this solution updates the values in place, avoiding any additional memory allocation. Therefore, the overall space complexity remains constant, or O1, regardless of the input size. When comparing this algorithm to the brute force approach, the advantages of the optimized iterative solution become clear. The brute force method uses a naive recursive formula, where t, n, equals t, n1, plus t, n2, plus t, n3. This approach results in exponential time complexity, O3 to the power of n, because each recursive call spawns 3 additional calls, leading to an explosion in computation. Furthermore, the space complexity of the brute force method is O(n), as the recursion call stack can grow up to n levels deep. In contrast, our optimized iterative solution avoids all redundant computations by calculating values sequentially in a loop. This drastically reduces the time complexity to O(n), and the space complexity to O1. By eliminating the need for recursion and additional memory, the iterative solution is both exponentially faster and more space efficient than the naive approach. To further solidify our understanding, let's justify the big O complexities mathematically. The time complexity is dominated by the iterative loop, which runs for n-2 iterations, performing constant time operations in each iteration. This leads to a total time complexity of O(n). For space complexity, the algorithm only uses a fixed number of variables, regardless of the input size, resulting in O(1) space usage. When comparing this to the brute force approach, the iterative method is exponentially faster in terms of time and significantly more efficient in terms of space. Finally, let's consider the best, average, and worst-case scenarios. Since the algorithm always processes all terms from 3 to n when n is greater than or equal to 3, the time complexity remains O(n) across all cases. There are no variations based on input size or specific edge cases, making the time complexity consistently linear for any valid input. When working on the NTH Tribonacci problem, there are several common mistakes to watch out for. First, inefficient recursive calls are a frequent issue. If you use plain recursion without memoization, the algorithm will repeatedly solve the same subproblems, leading to an exponential time complexity. To fix this, implement memoization or dynamic programming to store intermediate results and avoid redundant calculations. Another mistake is forgetting to handle the base cases t_0, t_1, and t_2 correctly. Skipping these can cause runtime errors or return incorrect results, so always explicitly define these base cases as outlined in the problem statement. For larger n values, integer overflow can be a problem, particularly in languages like C++ or Java. Use appropriate data types such as long or long for these situations, or take advantage of Python's support for arbitrary precision integers. Finally, some may confuse the Tribonacci formula with the Fibonacci one. Remember, the recurrence relation for Tribonacci is t_n equals t_n1 plus t_n2 plus t_n3, not the Fibonacci formula. Misapplying this can lead to completely incorrect results, so always double-check the problem definition to ensure you're using the right formula. Another frequent issue is unoptimized space usage. Many solutions use a full-sized array to store all intermediate values, but this is unnecessary since only the last 3 values are required at any given time. Instead, you can use 3 variables to iteratively compute the result, reducing the space complexity from O(n) to O(1). Now, here are some interview insights to keep in mind. First, recognize that Tribonacci is essentially an extension of Fibonacci, so interviewers expect you to adapt familiar strategies such as dynamic programming or iterative solutions. Start with a brute force approach and then optimize it for time and space, ensuring you clearly communicate your thought process throughout. Be prepared to handle edge cases like n=0, n=1, and n=2, as well as very large inputs, since these test both correctness and efficiency. Additionally, discuss trade-offs during your interview. For instance, while recursion is easier to implement, it's inefficient compared to iterative solutions, which require careful handling of variables. Finally, keep in mind language-specific considerations like integer overflow in statically typed languages, and choose appropriate data types or libraries to address this. The Tribonacci problem also connects to several related problems that you might encounter. For instance, LeetCode 509, the Fibonacci number problem, is a simpler variant of the Tribonacci sequence and a great starting point. Another example is LeetCode 70, climbing stairs, which involves a Fibonacci-like dynamic programming approach for counting steps. LeetCode 198, the house robber problem, builds on similar recurrence relations and is a classic dynamic programming challenge. Finally, LeetCode 878, the nth magical number, is another sequence-based problem that requires optimization techniques, making it a valuable practice problem. Now, let's explore alternative approaches to solving Tribonacci. Memoization is a straightforward method that's easy to implement and intuitive for beginners. However, it does have higher space usage due to the recursion stack and the memo table. Iterative dynamic programming is another option, offering both time efficiency with O(n), complexity and space efficiency with O(1). It's slightly more challenging to implement compared to recursion, but it's a highly effective solution for this problem. For more advanced optimization, matrix exponentiation is a powerful technique to consider. It reduces the time complexity to O log n, making it ideal for handling very large values of n. However, this approach is more complex to derive and implement, and it's often overkill for smaller input sizes. Another theoretical approach is the closed-form formula. If you can derive such a formula, it allows for constant time evaluation, which is highly efficient. That said, closed-form solutions for Tribonacci are rarely feasible due to the complexity involved in deriving the formula. While these advanced techniques can be rewarding to explore, they're generally applicable in specific scenarios where high performance is critical, or the problem constraints demand it. Great job making it to the end. To summarize, we tackled the nth Tribonacci number problem, explored recursive and optimized solutions, and highlighted key takeaways like the importance of dynamic programming. Thanks for watching, and don't forget to like, comment, and subscribe for more coding insights. Keep practicing and happy coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding! Great work! Today, we tackled the nth Tribonacci number problem, learning both recursive and iterative approaches. Remember, optimizing for time and space complexity is key to efficient coding. Keep practicing, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!